Okay, we have an f of x and we're supposed to find concavity intervals and inflection points. It's a combination of trig and a linear term, but as you're going to see in a second, the linear term does not matter to the concavity. The short explanation for that is that straight lines don't have any concavity, so when you discuss concavity, they kind of disappear. And the other explanation for why it's not going to matter is, well, you'll see in a second. We need a first derivative before we can get a second derivative. And our first derivative is 5 times, what's the derivative of cosine? If you haven't done trig yet, I will remind you, this might be on your formula sheet. The derivative of cosine anything is negative sine of anything times the derivative of the anything. So in this case, our derivative for cosine 2x is going to be negative sine 2x times the derivative of 2x. That's the chain rule happening. And then we get minus the derivative of x is just 1. No, that's way too horrible to leave that way. For coefficients, we have 2 and 5 and a negative sign, so negative 10 sine 2x minus 1. That's our first derivative. For our second derivative, the derivative of sine, as you may remember, is cosine, positive cosine x dx. So when we're doing this one, we get negative 10 cosine 2x. Then the chain rule says do the derivative of the 2x thing now. So we get a 2 popping out. Then we do the derivative of negative 1, which is 0. And this is the other reason why that linear term ended up having no effect. It has a little bit of a first derivative. It has no second derivative or anything deeper than that. So that's how the math tells us that straight lines don't do anything to your concavity because they aren't concave. They don't bend up or down. We can pretty this up slightly and get negative 10 times 2 is negative 20 cosine 2x. That's acceptable. And now if we're studying concavity, we want to look for places where the second derivative is 0 or where it's undefined. Well, undefined doesn't happen. The cosine function is defined everywhere, but it's certainly 0 in a bunch of places. We can do negative 20 cosine 2x equals 0. Divide by negative 20. And so the question is, the cosine of what gives 0? Where's the x-coordinate on the unit circle 0? Well, that can happen at pi by 2, or 90 degrees. It can happen at 3 pi by 2. It can happen at 5 pi by 2. It can happen at 7 pi by 2, 9 pi by 2, every odd pi by 2. Now, some of these are probably superfluous, but let's find out. We finish this by dividing all of them by 2, and we get that some of our possible solutions are pi by 4. We have this restricted domain up here, but pi by 4 does fall into it, so yes, that answer's a keeper. This next one comes out x equals 3 pi by 4, and that's a keeper also. That's in the range 0 to pi, and I bet you this next one's too big. X equals, that'll be 5 pi by 4, which is like 1.25 pi, which is more than pi, so too much, time to stop. So when we're analyzing our second derivative, we have two interesting or critical values, pi by 4 and 3 pi by 4. And our second derivative is just one piece, so I don't have to do a whole bunch of rows here. I can just evaluate the whole thing at once. Our second derivative is negative 20 cosine 2x. Be careful when you're doing a sine table that you don't forget about constants like this. I know we divided out the negative 20 and it made solving this easier. We only got away with that because there was a 0 on this side. When you're looking at the signs of the second derivative, it matters a great deal that there's a negative 20 parked out in front of it. The 20 doesn't really matter, but the fact that it's negative sure does. That's going to affect the signs that we work out along here. So Please, by all means, junk this minus 20 when you're solving for roots, but be sure to include it. It is part of the second derivative when you're doing your sine table. Please and thank you. All right, so if we have an angle here of, I don't know, 1 degree, take 1 degree, double it, that's 2 degrees. The cosine of 2 degrees is something positive, multiply it by negative 20, and it's negative now. Pi by 4 is 45 degrees. Double that, you get 90. Cosine 90 is 0 times negative 20 makes no difference. It's still 0. If we're here, what's between? We could use pi by 2 for the number between these two values, so 90 degrees. Double that, you get 180. Cosine 180 is negative 1. Negative 1 times negative 20 is positive. 3 pi by 4 is 135 degrees. Double that, you get 270. Cosine 270 is 0 times negative 20. Doesn't matter. Still 0. If this is, say, I don't know, 150 degrees, something bigger than 3 pi by 4, double that, you get 300. Cosine 300, we're in quadrant 4, the bottom right, so cosine's positive, times negative 20 comes out negative. So our intervals of concavity, of course, are that it's concave down below pi by 4. Here, I'll write this out. I don't always write them out, but I should do one occasionally. It's concave down from minus infinity up to pi by 4, and also from 3 pi by 4 to plus infinity. It's concave up in between here, so from pi by 4 to 3 pi by 4. And for points of inflection, we have, this is a point of inflection because it goes down through this point and then up. And this is also a point of inflection because it transitions from concave up to concave down. So we should get coordinates for those, and I'm going to have to carve out some space to make that happen. Our points of inflection, POI is a common abbreviation for that, is, well, the first one's pi by 4, and if we want a y-coordinate, we have to go back, not to here, this is for concavity, not to here either, this is for slope, up to here if you want an actual position. And we put in pi by 4, we get, pi by 4 is 45 degrees, double it, you get 90 degrees, cosine of that is 0, times 5 is still 0, minus pi by 4, sorry, comma, minus pi by 4. And the other one is 3 pi by 4. I think that same thing is going to happen here. 3 pi by 4 is 135 degrees. Double it, you get 270. Yeah, cosine is 0 times 5 is still 0, and then you subtract that number, so minus 3 pi by 4. So the trig part ended up kind of canceling here. That's interesting. These points are not only zeros for the second derivative, it turns out they're also zeros for the original function, at least this part of it, because they both contained cosine 2x. That's why the cosine part kind of dropped out, and all we ended up here, we ended up with this function behaving like y equals negative x at the 2 points where the inflections happened.